Everyone, welcome to the very first lecture of AI Simplified series. In today's lecture, we're going to talk about some introductions on artificial neural networks. So what you should expect in this very course is you should expect to learn a little bit of the history of artificial neural networks, when it was started, what happened to it, and where we are now. Then we're going to talk about the simplest architecture of neural networks, the Perceptron architecture, and the learning rules. And we are going to spend a little bit of time on one of the most powerful algorithms that revolutionized neural networks, back-propagation. And then we talk about multilayer perceptrons, and then discuss a little bit about different types of activation functions, wide versus deep neural networks, and we discuss if depth is better, if you have many layers, or if width is better, and lastly, some hyperparameters to tune. This lecture is mainly about introduction. Beside backpropagation, we are not going to get into too much detail of the thing. So for more advanced people who are seeing it, maybe you should skip this course. But if you want to learn a very high level about neural networks, and when they start, that's a very good starting point. And I think the backpropagation slides would be very helpful for those of you who have heard about it, really struggle to understand what it actually is. And so stay tuned. Some acknowledgement. My lesson plan is very much follow the sections on this book, Hands-on Machine Learning with Scikit-learn, Keras, and TensorFlow. That's an excellent book. If you can afford, please buy the book. This lecture specifically, the lesson plan is designed based on chapter 10 of this book. I highly recommend it. Right now, I don't have the permission of the author yet to publish the Python portion of it, because if I want to have a lecture, it will be based on the Python portion of this book. But if you have the book, you can have access to the Colab and GitHub of it. I think you don't need to buy the book to have access to those parts, but I highly recommend you get this book. I cannot say enough good things about the book. Okay, so let's get started. So let's see, what is the inspiration behind artificial neural networks? Like many inventions in human history, the invention of artificial neural networks have something to do with something is happening in nature. For example, if we look at the brain structure, we will see there are so many neurons that are connected. That is why the schematic of this specific algorithm, artificial neural network, it very much resembles that. But as many other things, we are inspired by nature, but the functions are completely different. It's not exactly mimicking that. For example, we have developed submarines based on whales, but we can argue that it has nothing to do with whales. It just looks the same. And you can say the same thing for artificial neural networks, to the extent that so many of the researchers have argued that we should change the name of neurons to units to distinguish between that. A little bit of history. The history of artificial neural networks is very rich. It started in 1943, so it's around a century ago. It's 80 years ago. That's when it was started. It tracked a lot of attention, but in 1960s, because of some of the technical difficulties, convergence of the algorithms, and some other technologies, it became less and less, people become less and less optimistic about it. People start forgetting about it. And then in 1980s, a very interesting algorithm called back-propagation revolutionized it. So the enthusiasm about these algorithms started increasing again in 1980s. But in 1990s, there were some state-of-the-art machine learning algorithms which were theoretically sound. People could easily use, like SVMs, which we have discussed in previous lectures, previous series of lectures, became the state-of-the-art algorithms back then. So people say, okay, maybe artificial neural networks weren't that cool anyway. And for a long time, researchers who were working on artificial neural networks became um, uh, were not too proud of what they were doing. And in 2010s, there were some new inventions and data availability and increasing computation power that again changed the perception about artificial neural networks. But the the word artificial neural networks didn't have a positive connotation among researchers, so people changed the name to deep learning. So you start hearing about deep learning, tomato. And then in 2016, a breakthrough in by Google, who beat the Go champion, changed the perception again about what artificial neural networks are capable of doing, because it went beyond what we knew about this game by playing against itself. So that for the first time, it used a new gaming strategy that were not known to human before, and because of that, people saw that the algorithm can actually extrapolate. And in 2017, Google published a very amazing paper called "Attention is All You Need." That's actually self-attention is something we're going to discuss in a few lectures from now. That revolutionized LLMs. Whatever we see right now, all of the crazy progress that we see in AI is coming from here. And in December 2022, which I cannot believe it was only 14 months ago, ChatGPT showed what LLMs are capable of, and everything else is just history. So a little bit of side note. That's for those who want to know why this time AI is different than ever. It's because for a long time in human history, AI advancements were following. Sorry, not AI advancements. Technological advancements were following something called Moore's law, specifically in computation, which was saying that every 18 months our computation power is double for the same price. That's called an exponential growth that we are very used to. For example, here is an example of what exponential growth means. Imagine you put $1 in a bank and you receive 50% interest rate on it, and you keep the principal and the interest and you compound it. After 20 years, your compound return is 300 over 3,300. That's 3,300 return. That means in 20 years, our computation is 3,300 times better for the same price. And the Moore's law have a very, very consistent profile. But what is happening in AI that makes a difference is an exponent being an exponent and exponent function. There are few things that are affecting the performance of AI algorithms. One of them is availability data. The other one is computation. The last one is number of parameters we use. And it happens that these three can reinforce each other, and each one on itself follows Moore's law. So that is why the rate of growth also have some rate of growth. So now imagine, for the previous example, you have $1 in bank, you receive an initial 50% return on it, and the interest rate on itself increases by 20% every year. So you get 60% next year, next year you get 72% return, and so on and so forth. So now let's see, after 20 years, how much compound return we want to have. Just make a guess, because the number I'm going to show you did blow my mind. I think it will do the same to you. The answer is $3.6 trillion. That's the factor of $1 billion difference between the two. And that is why this time around the AI revolution is going so fast that we cannot catch up because of that exponent of exponent growth. The best of it is yet to come, but you can see the magnitude of difference in it. So now let's look at the easiest architecture in neural networks, which has been around for, as I said, many years, many decades, and that's the perceptron architecture. The idea is you have some features like x1, x2 through xm, and you want to make a prediction whether a category is whether these features belong to a category or not. So let's say the features you have is how tall the species is, what is the weight of the species, that's x2, xm, let's say, is how tall it can jump, and x0 is just the bias. So what will happen is these will input your model with the weights that you assign to it. So the weight times the height of the species, the weight times the weight of the species, the weight times how much the species can weigh, and so on and so forth. And then in the z function, we have the sum product of it. Then we pass it through something we call activation function. So let's say we sum product of these outputs is 5, let's say. So if in this step function that is more than 5, we assign the category 1. We say, oh, this species is a cat. If it's below, let's say 0, we say, oh, this is not a cat. So the step function works as follows. So you just multiply all of the features by their weights, then you look at the step function. If it's positive, if this sum product is positive, you say, oh, it belongs to this category. If not, it doesn't belong to that category. So that's as simple as that. And for this activation function, we use step function as an output. We can change it to anything that we want. We can have a sigmoid function, and for those of you who have had data science courses before, sigmoid function was the same function that we use in logistic regression model. So we can pass through that sum product, that linear combination of inputs and their weights, to a sigmoid function, and the output will be probability that this belongs to a class. We can use hyperbolic tangent activation function, or something that became more streamlined, rectified linear units, mainly in like end of 2000s, like 2008, 2009 to 2010s, early 2010s. I cannot quite recall when, but when I first heard about it, I said it doesn't make any sense for a reason I'm going to explain later. But it turned out that in reality it works very, very well, which is, it is 0 before 0, and then after that is just a line. So you can see it on, you can see all of these activation functions in these graphs. So what is important for activation functions, as we're going to see in backpropagation algorithm, is the first order derivative of that, or gradients of them. So the gradients of these activation functions, for example, sigmoid itself on the left hand side graph is the blue curve. As you can see, when it becomes like -2, -4 and below, it becomes it tangents toward -1. Sorry, I made a mistake. The sigmoid activation function is the green one, dotted green one. As you can see, when it's very, very small, like -4, it tangents around 0. And then when it's like very, very large, like 4 or 5, it tangents toward 1. So if you look at the gradients of it on the right-hand side, the first order or derivative of that on the right-hand side, what you're going to see is what we just explained. So the gradient of that function, the grid function, is very, very small on very negative numbers and very, very small on very large numbers. Tangent hyperbolic one is even more extreme on the extreme side, so it becomes like more close to 0. And as you can see in the ReLU, rectified linear units, the first order derivative is 0 when it's before 0, and it's constant after. That's one of the issues of rectified linear units, is it doesn't have any derivative at 0. So going back, for that step activation function, you can replace it by anything you want, any activation you want. There is no theoretical limit what you can use. Of course, most of them are not useful, but you can replace it with anything you want. And one thing is, when you're training your algorithms, what you do is, let's say you have 1,000 observations, you have 1,000 training data. You usually do not update the weights of the algorithm based on all of those 1,000 observations at the same time, because teaching an algorithm, neural network, is basically teaching the algorithm to learn weights, because as soon as it learns those weights, W0 to Wm, everything else is already set up. Z is just some product of that. Activation function is a fixed function. You just pass that Z through that. So in order to train an algorithm, you usually do not pass all of the data at the same time and then update the weights. You usually divide your data in very, very small chunks. We call them batches. So let's say for this one, we have 10 batches of 100 observations. That will encompass all of the training data that you have. And each time you pass 100 of this data to your model, to your neural network, you measure the error, you update the weights, and then you go to the next batch of 100 observations. Then you go to the next batch of the observations. By the time you have reached the end of those 1,000 observations in this example, we have gone through one epoch of training. And then if you want to train your model more, you see that it's not being trained yet, you go back, you start from the first batch, second batch, third batch. And by the time you reach to the 10th batch, again, you have passed through this data in 2 epochs. So don't get confused when you hear about epochs. Epochs is going through the whole training data once using those batches. Those batch sizes, we can say it's a tuning parameter. It's a debatable fact how big they should be actually. And surprisingly, there are some debates. Some people say, oh, batch sizes between 20 to 64 is optimal. Some people say, no, the batch size will be as big as what your computer is capable of handling. This is debatable. And one of the tuning, I would call it a tuning parameter to decide what the batch size is. But for most applications, if you choose any batch size by using a correct learning rate, I know that these terms are alien for now. By using a correct learning rate, you can achieve similar results, I would say. So I think batch size and learning rate hyperparameter tuning are the same thing. Sorry for throwing in new terms that we haven't discussed yet. Bear with me, please. So in next slide, so what I'm going to do next is I am going to go through the most fundamental algorithm in training neural networks. It's called back-propagation. And to do that, I'm going to go through a numerical example. What I ask you is pause the video right now, have a pen and paper ready, and try to do what I'm doing alongside me. I promise you, if you can do it alongside me in the next few minutes, you will learn backpropagation by heart. When I learned backpropagation, that's a side story. When I learned backpropagation algorithm myself in 2003, my professor did exactly that to us. Actually, in our final exam, he asked us to update the weights using backpropagation algorithm on a model that had 2 layers. And back then we didn't have computers. We didn't use computers. We were using just calculators to update it. But since I did that time, more than 20 years ago, and I knew how to do it by hand, it always stuck with me. So I'm not scared of this one. So if you can follow along and write down things with me, that would be wonderful. So have a piece of paper available, please, with pen, and I see you soon. All right. So we want to introduce our very first simple neural network here. Our neural network only has 2 inputs, x1 and x2, as identified here. And it's a fully connected network. It has 2 hidden layers, and its hidden layers, we have a simple activation function, which is an activation no one ever uses. That's the most stupid activation function. And please bear with me, because that's if knowing that is going to help us to make the derivatives easier, and the math will be easier to follow. So these will be fed here, and in each of these neurons, whenever we have an input, the input will be the sum product of all of the inputs based on the weights that we have. Then it passes through that activation function, which is z squared, and then once it's done, the output would be
multiplied by these weights, go to the final node where the final is just simple sum product. So in order to make sure we understand what is going on there, so let's make sure we write things down. So for example, Z1, which is identified here, is W1 times X1 plus W3 times X2 plus its bias, which is B1. And G1 will simply be Z1 squared. And then Z2 is simply W2 times X1 plus W4 times X2 plus B2. And G2 is simply Z2 squared. So let's plug in numbers there. So Z1 would be, with this definition, would be simply 1 times 1 plus 3 times -1 plus 1, which is -1. G1 would be -1 squared, which is 1. Z2 would simply be 2 times 1 plus 5 times -1 plus 3, that is 0. I intentionally use some numbers to make life easier. And G2 is simply 0 squared, which is, again, 0. It's not ideal to use numbers that add up to 0, to be honest, because of some of the complications that we would get. But here, since we only want to update the weights on top, things will be easy to have one of the branches give us 0. So Z3 here is simply 0.5, would be W, let me write it down first, and then we added, oh, by the way, I forgot to add a bias here, so let's assume the bias here is 2. So Z3 is simply G1 times W5 plus G2 times W6 plus B3, which is in a sense, G1 was, we calculated that to be 1. So 1 times 0.5 plus -1 times 0 plus 2. So the answer is simply 3.5. Sorry, 2.5. So that's the final answer of our prediction. So Z3 is our Y prediction. All right, so imagine we had an example that, let me make sure we have done everything correctly. Yes, okay, perfect. So now imagine we are living in a world that we know that our real prediction, so real Y, what we were trying to predict, our observation, was 3.5, okay? And let's say we are using a square level of our cost function. So we define our cost function to simply be our predictions minus our observations squared. So in this case, that would have been 2.5 minus 3.5. So we predicted 2.5, reality was 3.5. So that squared would be 1. Okay, perfect. So now, what is important is this step is to be able to calculate the portion of the error can be how much each of these weights have contributed to that error. And in order to be able to understand it, we should know the partial derivative of cost with any of those weights. So let's just start with the very easy one. So let's say, so remember, Z3 and predictions were the same. So what is the partial derivative of cost with respect to W5? So let's say we want to update the weight of W5. So as I said, we need to know this partial derivative. We need to be able to estimate that. And that is pretty simple and straightforward. Sorry. So we do not know that directly because cost has prediction in it, and the prediction itself is a function of W5. But we know a very powerful law in mathematics and algebra, and that is when you can run a chain rule. So that will be partial derivative of cost versus partial derivative of your prediction times partial derivative of your prediction divided by partial derivative of W5. So these are equivalent. So what is the partial derivative of cost? This is our cost function over our prediction. That's a quadratic function. Very, very simple. So that's y prediction minus y. Times, what is the partial derivative of prediction? I should have written y prediction. What is the partial derivative of y prediction with respect to W5? So that is G1. So very simply put, so that is 2 times, our prediction was 2.5 minus 3.5. And our G1, we already calculated that was 1 here on top. Okay, so right there. Okay, so that's times 1. So that is, if we just simplify things, is negative 2. So what we are going to do in order to update it is using an algorithm called a stochastic gradient descent. It's called gradient descent. And in order to do that, we usually do it this way. So we say, okay, so I know the this is the effect of this weight on this cost. So I'm gonna go in that direction. Since I'm minimizing it, I go against that direction. So what we are going to do is we write W5 new, or let's say updated, is equal to our old W5 minus eta. This is a learning term, times this partial derivative. There is a lot of discussions of how to find this learning rate, but for now, please accept it from me that we are using it using a number like 0.0. This is for now is arbitrary, but later on we learn the science behind these things. So let's say we're using 0.01. So that would be our old W5, which was 0.5, minus our learning rate, which was 0.01, times what we found for this partial derivative, which was negative 2. So our new updated rate would be 0.52. Perfect. As you can see, you can easily update W6 and so on and so forth. But since G2 was 0 in that case, that would have been 0. Again, that's one of the reasons we don't want to use something that add up to 0. But in this case, since we are only updating the top part, that's totally fine. A side note, one of the reasons we have to make sure we use random numbers at the beginning of initiation is these things, not to get into 0 numbers like this, because the weights are not going to get updated. So of course you can have 0 for different inputs. This is only one example. For other observations it doesn't come to 0, but in this example, if I want to update the weights based on 0, I wouldn't be able to. Okay. Cool. So what should we do next? So how can we update, say, W1? W1 is so far away from here. So what should we do with that? Let me go down and only focus on part of this graph. So what I'm going to do is I'm going to only cut this part of the graph and just bring it in. So let's go down and redraw our neural network, this time only partial of the neural network, because we only need that part that we need. So that was Z1 and G1, and this was Y prediction. And I remember we had like some other things coming in, but for this example, it's roughly irrelevant. Okay, so this is Y prediction. Okay, so and in our input we had like three inputs. We had the bias, we have W1, and W3. W1 was coming from X1. This one coming from X2. Okay, cool. So as a reminder, so that we don't miss track of anything. So let me write down the important formulas that we knew. So we knew that cost function was y prediction minus y squared. We knew that y prediction itself, in previous example we called it G3, was basically G1 times W5 plus G2 times W6 plus B3. Let me make it cleaner. Okay. And this is W. And we knew that G1 was simply Z1 squared, and we knew that Z1 was X1 times W1 plus X2 times W2, X2 times W3 plus B1. And again, I should emphasize that I intentionally use this activation function because that's a quadratic function. It's easy to estimate the first order derivative of that, and life would be significantly simpler if I used that. We could have used any other activation function, but it wouldn't be as easy to follow the partial derivatives. For illustration purposes, I think that's fine. So what we need now is to find the first order derivative, the partial derivative of cost with respect to W1. You see that it's like far back of this network. So how can we do that? Again, the chain rule is our friend. In order to do that, we need to find partial derivative of cost with our y prediction, then partial derivative of our prediction with respect to G1, then partial derivative of G1 with respect to Z1, then partial derivative of Z1 with respect to W1. It may look complicated, but there's nothing complicated about that, honestly. We just follow the chain rule. If we have neurons that are thousands of layers behind that, again, that's the same thing. And it's pretty easy to estimate those. There's nothing scary about them. So this one we already calculated. That was 2 times y pred minus y. Y prediction over G1. So here we have the formula, as you can see, and that is easily W5. The other parts of it is just linear. So we just write W5. Partial derivative G1 with Z1 is 2Z1. It's a quadratic function, so 2Z1. Then partial Z1 with W1 is simply X1 here. Simply X1. So we just plug in numbers. So 2 times 2.5 minus 3.5. W5 was, I think it was 0.5. Yes, it is 0.5. Okay, so let's go back so that we make sure we bring in the right numbers. Yes, W5 was 0.5, as you can see here. G1 is 1. And Z1 was -1. Okay, cool. So let's go back. Okay, 2 times Z1, so that will be 2 times -1. And X1 was, let's see. Okay, so I like to write multiplication this way, to be honest, because of complications. That makes it life easier. Okay, perfect. And then we have X1. X1, our input was 1. Let's see. Let's double check. Yes, X1 was 1. So if you just multiply that, that will be 2 times -1. 2 times 1 is 1. So these are all -1. So the whole thing is 2. So how do we update W1 now? Now we know this partial derivative. So W1 updated would be equal to whatever W1 was minus eta. which is our learning term, learning rate. We assume this 0.01 and times this partial derivative. So that will be W1, again, as a reminder, was 1. So we want to update that. So 1 minus 0.01 times 2. So that will become 0.98. And as easy as that, we now know how to do backpropagation by hand. That's beautiful. And as a reminder, it's as easy to do it for any layers even behind it. If you have dozens of layers, the math is the same. It looks complicated, but it's very calculatable. And by that, we move back to our slides. So as we talked about backpropagation, we saw that it's a relatively easy algorithm to implement. We did it by hand, but obviously in computers we don't do it. And generally speaking, it's a very good candidate to do things in matrix algebra. And as soon as you can vectorize things, use matrix algebra, life is significantly easier. So let's go through the steps one more time in a more formal way. So what we did was, in each mini batch is passed through the network. In the example we worked on, there was only one observation which was passing through the network, and then we were measuring the error. But generally, you pass the entire mini batch to it and make the predictions about every single observations in that batch and compute the error. That is called forward pass. When the predictions are made, this is called a forward pass. Then for each one, as you saw, we estimated the error of those observations. Then we saw how much of the output bias can be attributed to each of those weights and connections. I shouldn't have used the term attributed, better say how much of an impact each weight has on this error. And then when we compute this contribution using our chain rules, we propagate the error gradients backward. As you saw that our first using chain rule, we were multiplying a lot of partial derivatives. And then using gradient descent, remember we used eta, which was learning rate, we update the weights. And here is again another breakdown of the same thing we talked about. Since we've already talked about that, I'm not going to get into too much detail of this one. That's more representation of it. I borrowed that from a Stanford course. But two things to remember before we move on. The first one is you should always initialize your weights completely at random. So do not use like 0 for weights. Otherwise, it will be almost impossible to update them. So just use initial random numbers there. In our example, for example, in that one observation, I think the bottom layer would give us the output 0. Zeros are not well tolerated by neural networks and updates, and we don't want to have like very large numbers either. So we initialize these weights. This is a technique that we're gonna talk about more in future lectures. We saw that choosing the right randomized numbers with specific standard deviations can actually help the algorithm to learn faster. That was one of the breakthroughs that happened during the last 2 decades. And the second thing, we should normalize our data, meaning that we project all of our data to have the same scale. So if you have some observations which have a scale of 1,000 and another one 1,000,000,000, obviously your model and weights cannot be adjusted as good. So we should always normalize our observations, let's say to map them between 0 and 1 or negative 1 and 1 to assure the algorithm works well. So these are the 2 notes I want you to take with you. So the next thing we want to discuss is how can we use this architecture if we have more than one output. For example, let's say based on the weight, height, how much an animal can jump, we want to predict whether the animal is a deer, a cat,
or a dog or many other categories. It's not a dichotomous outcome anymore. So in the previous example, where assumption was whether it's a dog or cat, for example, if it's a cat or not. But what if we have more than one observations, more than one category? We have like 10 categories, 20 categories. We want to make predictions for that. And these categories, let's say, are in this example, are independent. And the summation of that, so the union of that will encompass your word. So how can we translate those activation function numbers, let's say, from coming from logistic regression number in one term? The trick is using a function called softmax. Softmax basically exponentialize the output of each of those output layers and then divided by summation of those exponents. This way, you can actually see the probability of each class. For example, you see that probability of that being cat is 10%, dog 80%, and let's say deer another 10%. So the best guess is it's a dog. So that helps you to scale the probabilities in a way that it always adds up to 1. So that's a small trick. We're going to talk more about it in the future, but generally speaking, softmax, we had it before too. So I think in the previous series of lectures that we had in ISLR textbook, we talked about the fact that you can have multiple classes in multinomial regression models, and the tricks we were using were almost the same. Another architecture that I want to discuss, which is interesting, it's called wide and deep neural networks. That is coming from a publication that is published in 2016. We can have cases that your input layer goes through many like hidden layers before it get into the output layer, but we also feed the input layer to the very last layer too. So we have more than. So not only we can learn very deep, very, very deep patterns that is coming from your input layer, but also we can preserve the simple relationships of the features. And that is the way you can have best of two worlds. So the reason I put it here to show you that in artificial neural networks, you can have any different type of flexibility that you want to create, the way you want to play with input, it's possible. And as we mentioned before, we can have absolutely two different outputs. In the previous example that I talked about, softmax, here, we had similar output. We just wanted to predict the category that some observation belongs to, let's say cat, dog, deer, and many, many, many things. These are independent categories. The union of them would be the same domain. But imagine now you want to train a multi-layer perceptron or multi-layer neural network that wants to predict two different things. For example, first you want to predict whether the image that you have showed to the algorithm is cat or dog, and then the second prediction is whether this is the animal is white or black. As you can see, these two observations are independent, but the union of them are not. I made a mistake in terminology. Here, the outputs are not independent. You cannot be a dog and cat at the same time in this case. But here, the union of them is not necessarily the same object. For example, you can have a category for the animal, the type of animal you have, a category for the color, a category for how many eyes the animal has, and so on and so forth. So as you can see, these models are extremely, extremely, extremely flexible, and you can design any level of complexity that you can give any level of complexity that you want for these models. So there are some questions that we need to answer. And I want to end the lecture by notes on that. The first one is, do we benefit from designing like fewer layers of hidden layers? For example, in the second layer and third layer of this neural network are hidden layers. Do we benefit from having less layers, but each layer be very wide, meaning that we had many, many neurons on it, or we benefit from deeper ones and narrower ones. For example, instead of having 2 layers, we have 10 layers, but each one of them only have like 2. Which one give us better performance? Generally speaking, you can learn any pattern with either of them. There is no theoretical bound to it. So you can have wide enough network or deep enough network to learn any pattern that you want. But in practice, deeper layers are usually preferred to wider layers, and it's because of the computation. It uses exponentially fewer computation to get to the good enough answer. I hope that you already know the answer to this question. So how do we learn the weights? So in any network, we can have any flexibility that we want. We have it as wide as we want, as narrow as we want, as many layers as we want, anything. How do we learn the weights? Excellent question. The answer is backpropagation, and we showed you how simply it can be done. Hopefully you followed along using pen and paper. And then, like, another thing we need to discuss, and we're gonna discuss thoroughly in next lectures and further lectures, is how do we know what is the optimal level of architecture that we can have? So what are the things we can play with in a network to get to the best architecture, best performance? What are those? So the first one that we need to tune on is number of layers. How many layers do you want to have? How many neurons in each layer? So let's say you have a very deep neural network. How many neurons do you want to have there? 2, 3, 4, 5, 6. If you have too many layers, it will overfit, hard to train. You have too few, you cannot generalize, and so on and so forth. The other one is learning rate. I think in the place that we were working on backpropagation, we showed that learning rate can have some effect. So how do we what learning rate should we use? Again, that's a discussion that we're gonna definitely have in next lectures. The other one is what type of optimizer do we use? We're gonna see there are many different optimizers out there. The way that we update our weights, we use a gradient descent algorithm there, but there are many more that we can use. The other one is batch size. Do we want larger size or smaller size? And as I alluded to, there is debate there. Some researchers say the batch size should be very small. Someone say it should be very large. And but it seems like learning rate and batch size are two dependent tuning parameters. So depending on which learning rate you use, the optimal batch size will be different. The next one is activation function. We have covered a few activation functions like rectified linear units, hyperbolic tangent, sigmoid, and a step function. And I used a very funny activation function in the numerical part of the course just to make it easy for us to follow the course. That activation function that I use there is no one ever uses it. And the next one is number of epochs. When should we stop the algorithm? Should we go forever? Should we stop right away? Actually, there are algorithms that we can use to see when we stop. Number of times you go over all of your data and feed it and train it and update your weights is a tuning parameter. There are algorithms there are methods that we can use the optimal number of epochs, and we're gonna talk about it later. All right, thank you so much for following along. I hope that you learned a thing or two about neural networks. Specifically, what I want you to take from this lecture is the backpropagation algorithm. If you were able to follow along using paper and pencil, I am sure this is a concept that you will never forget. Again, thank you so much, and I'll see you in the next lecture.